Guys, thank you very much for joining this workshop. And we're going to talk in the next hour and I hope 45 minutes. Maybe we'll extend a bit. And I hope there will be a lot of questions eventually because I'm looking forward to talking about this topic. And we're going to cover the continuous ML stack idea and concept that's being evolved in the last few years, and we'll just show quite a simple way to implement it, just to understand the paradigm itself, the concept itself. So again, we did some oversimplifications in the code that you're about to see and write. So as a data scientist, you'll probably feel a bit inconvenient with, I don't know, running cross-validation of 2 folds and stuff like that we did here for compute. But just bear in mind that the implementation is not the main goal here. It's just to understand how simple it is to implement a robust ML infrastructure within your organization. So a bit about us. At Superwise, we're developing a platform built for scaling MLOps and monitoring them. So pretty much if it was easy enough to monitor 10 or 20 or 40 models in production with the data science team, the way we see the future and how all the industry is walking towards is that in few years' time, automations will be able to generate more and more models for subpopulations and some different scenarios within the data sets. And then when you scale things up using automations, then you cannot really keep track of all those models in production. And sometimes anomaly detection scripts and some other usage implementations for it may get a bit complex because they are too coupled to the actual model. And this is where we see ourselves. We're completely agnostic to the model. We try to build you a monitoring or observability platform for as many models as you can imagine, pretty much. About me, I've been in the industry for like 6 years now. I worked for NVIDIA for a while, and then in Fiverr, if you guys know, in Tel Aviv. And in the last 6 months, I'm with Superwise. And hopefully I'll stay there until the pension. Okay, feel free to ask me questions during that. Raise your hand, and I'll try to reply. But keep in mind that I will leave time for questions in between. There's a lot of things to cover in this talk, and I want to leave those gaps for talks. So we can skip this one because I guess most of you you saw on Wova that I send just the repositories that we will be using, but it will be in the notebook shortly. Before we go to the technical part, maybe just have 3 or 4 slides about why I'm standing here on the stage and what basically drives this entire concept of continuous training. So the transition from pure software, I would say, systems into ML-based products and systems have brought some complexity in the way we monitor things, right? I've spoke to some of you yesterday, I guess, and the idea is that when you're deploying a service to production which is not ML-based, right? Let's say we have some service that can calculate the shortest path between 2 junctions, okay? The functionality and the monitoring of it can be very much deterministic. We can know in advance that if the exit code is different than 0, or if the CPU has exceeded 80% of utilization, or the memory is right now moving into swap space, then we know that something goes wrong, and it's very easy to put on alerts and all the other safety nets that we use in order to make sure that if something goes wrong, we can fix it as fast as possible. All those concepts still apply to ML-based products. However, a level of complexity comes in the picture. And what I mean by that is usually ML models in production, they fail silently. What I mean by that is if we have monitored our model in production, and we see that there is a distribution shift, for example, and the distribution shift is measured in 2.34 KL distance. Is that good? Is that bad? If the feature starts to drift, that might be within the thresholds that we have defined, and everything is good. However, some understanding at a point in time will not be relevant in a different point in time. And things constantly change, and the ongoing data in production and the data profiles keeps evolving, and it's hard to track and know it in advance. This is why it's stochastic by definition. And this is what brings us to, we need some sort of system or way to understand what's going on and try to fix it, or at least notify the people, right? Because if our bank, for example, will start to approve many loans because of a distribution shift in some marketplace, the people that will realize that something is wrong are the finance guys in the end of the year that will try to do all the reports and will see that, hey, we're doing something not good, like we're losing money, okay? And then it's very expensive. We need to bring it back to the data science team, have them understand the change, figure out how to fix it. It takes a long time. We want to skip it. We want to be as close as we can to real time. And then there is the reason, like why it gets so complex to monitor ML-based systems. So pure DevOps work would be to put all in the monitoring orientation, of course. DevOps is a huge, it has a very wide concepts, but well, when you have your DevOps team working with your production software engineering team, they are very much oriented to production. They know how to write production level software that will be able to scale. They will know how to put all the alerts and the ideas of what can go wrong and how to fix it. There is the CI/CD concept that help us integrate our changes in the code into production after we know that all the test has been in place and everything works fine and we're supporting backwards to everything. And when we talk about ML teams, they usually build from data scientists and researchers, right? And their orientation is a bit more experimental. They try different TDAs and they try to understand their features and run multiple experiments and hyperparameter tuning. And they live in a research area without much knowledge about production class software. In addition, the development is a bit different because when we're developing ML-based systems, we usually focus more on reproductioning, like the experiments, being able to reproduce the experiment, understand what worked well, what didn't, and now we can make like the best model right now and move it on to production. Testing have few more complexities to it because we do need regression tests for the software and integrations tests or unit tests, but we do need some data validations in order to make sure that the distribution of the data within our system that we build on, that we train our model on, will be as similar as it can be to the actual real world data. And we need also the model valuation and validation tests and some other stuff that makes it a bit more complex. Deployment gets way more complex, in my opinion, because you're not just deploying a package or a standalone service. You're basically releasing or you're deploying a pipeline. And we're going to see this pipeline in a few slides, or we're going to write one right now, and you'll understand that besides just deploying a service, we want to make sure that many, many different steps in the way are working correctly in order to have this service and the model that it's wrapping as robust as possible. And the last thing is the production one. I think I mentioned it before, is that the ongoing data profile in the real world change and affects our model. And this will say that this means that it's not just suboptimal coding that might break production. It's also because it's going to break someday because of model decays over time. So this is the changes that we are trying to, the challenges that we're trying to get over, and we'll see how we can try at least to fix them. So Google published an article about 5 years ago. Some of this talk based on it, and I do encourage you to go and read it. It's MLOps. You can look in Google MLOps, Google MLOps, and they define 3 levels of maturity, 3 maturity levels of ML systems, of ML infrastructure within organizations. So level 0, that was me 6 years ago. I got a task to develop a model that will try to predict how a unit within a chip in the VLSI industry will converge eventually. I had 176,000 features, and I had to clean it every time, and I had to come up with automation script that will help me find the correct model or the pickled object that I saved in some funny named folder within the system, and everything was super manual. I had no CI/CD in place. In order to deploy it, I had to speak to 3 different people from IT, from the DevOps team, and from some engineering team to help me bring up a service which will help me, unserialize the object I had and then put it in production. And eventually, nothing worked in production, right? The engineers came to me and told me, listen, it's not working. Like, it tells me that my unit is not going to converge, but it will, because there was a lot of complexity within that model. And this is where I started to understand that many good algorithms are not finding their way in production because of infrastructural complexities or challenges. Great. And of course, monitoring was not even a question. That was not in the place. Okay, and then there's the level 1. This is what we're gonna implement today. So there is some kind of symmetry in between the, I think you don't see it very well, so I think I have a second. That's great. So I kept this one. I hope looks better. So there are 2 main areas within that diagram. The first one is the experimentation area where the researchers and the data scientists lives in. They do work in front, like with a feature store or doing some data extraction. And then they're constantly running experiments using and doing data validation, preparation, training their model, working with some artifactory, writing their different pickled object or job libs. And eventually they feel confident enough that their model is good and they can deploy it to production. And then this is where the engineering part, the ops part comes in. And someone from the engineering, if it's not within an automation, need to come and take this pickle, run it through pretty much the same symmetrical pipeline or that have some common steps in it. Eventually make sure that the model is good enough for production, which is on different data sets than where the data science team worked on. And then if it's good enough, it can start deploying it. It can do it like in the deployment strategy can be just release and that's it. You can do A/B testing, you can do shadowing, you can do many different techniques in order to make sure that the model will eventually give you all the benefits of running in production without losing any performance. And after that, you can connect your monitoring into place and do many different types of monitoring. Like, I don't know if you guys have been in the talk yesterday about different strategies for retraining, but one of the ideas there, which we're going to implement today, is that if there is a distribution shift within the features and not necessarily on the prediction and the ground truth, like on what we're trying to predict, then if there is a big distribution shift on the features, we can actually trigger some action. We can have a webhook in place, and this webhook will reach some service that will help us deploy this pipeline again. This is exactly what we're going to do today. Back to the slides. Great. So, scope. The pipeline here is exactly what you've seen before. We're going to implement a small pipeline on Kubeflow. I chose Kubeflow because, to my eyes, that was the fastest way to show this concept. After that, we're going to validate and make sure that the model is good enough. We're going to upload it to some registry. We're going to write a small Flask application that will wrap this model. We'll take it from GCS, from the Artifactory, basically, use it, and then deploy to an endpoint using Google Vertex. Before we will deploy it, we will connect the monitoring. We will use Superwise to connect this endpoint and have monitoring policy in place. And then we're going to simulate some real-world data and see if it's going to work, that a trigger has been initiated and the retraining pipeline starts again. Okay. So yeah, Kubeflow, Docker image. We're going to serve it on Vertex, Superwise, and the webhook trigger. Of course, you don't necessarily have to use what I'm showing here. There are many different open source and managed tools out there, and I think one of the most exciting things that I can see in this specific conference is how big this ecosystem and how rapidly it's growing every day, and yeah, it makes me excited. I don't know about you. So just the images here are for the pipeline. You can use Jenkins, Airflow, and Argo. Argo is used under the hood in Kubeflow, one of my favorites. MLflow for a registry, Docker image for the trained image. Serving can be done with TensorFlow serving, Tensor serving, and Seldon. Seldon on here, they're amazing. Check them out. Monitoring using Superwise or many other vendors as well. And of course, Trigger. That's a webhook. It's unrelated to company. So just to focus, we're going to write a data extraction, validation, preparation. We're going to train a model. We're going to evaluate it, make sure that the train was good enough, and then we're going to run this model on a validation data set. In case everything will be good and the model will reach some kind of threshold that we defined, we will deploy it, and hopefully everything will play. This is the timeline, and I think we can move on to the actual notebook. Now, I haven't seen what every one of you is doing in his life, and I just want, like, it's mostly, the talk is mostly for ML engineers and software engineers that are trying to build infrastructure. And as I said in the beginning, if there are data scientists in the audience, forgive me for the oversimplification that we took for the concept. And great, let's start. You can open, you can run git clone on the branch of TMLS world from this repository. I send it on Wova, so you'll get this notebook. You can open it on Jupyter Lab, or you can open it in Google Colab. I suggest you opening it on Google Colab because the authentication will be more simple in front of GCP. And one tiny addition is that some of the people here that signed in with their work emails, not everyone, I wasn't able to give them permissions to GCP because Google did not recognize the email account, of course. I used Terraform, so forgive me for not letting you know in advance. I got the email list about an hour ago, and this is why it happened, but I'm more than happy to have a talk with each and every one of you afterwards and help you figure it out, like, and run it again on your own. It's easy and simple, you'll see. Great, so after you got this repo on your local computer, you can open it up, and we're going to start by defining the environment. We're going to need to talk to GCP. So there's a project ID which I created in advance. I created a project within GCP. The project ID is this one. And then we're going to import our import OS. And just to make sure, did you guys got the repo? Is everything okay? Just nod your head. Okay, great. Great, and then define your username that you're going to see. So I'll just write mine. Itay, that's my name. Use lowercase without any dashes or underscores. Okay, it's a bit sensitive to it. And then the bucket name that we're going to create would be this one. We're going to work on US Central 1. This is the region. Project ID and project number are already within the repo, so you can start and use them. And we're going to run it. Now, the authentication down below. We'll walk you through some simple authentication step. So you need to allow the Google Colab to authenticate with GCP, and then choose an account you want to connect with, and that's pretty much it. And now we're gonna run gclone. Now, okay, maybe a clarification. What happened with Google Colab is that Google is bringing up an instance, some pod that you can work on. It's a VM basically. So you have your own separate environment, and this is why we need to do all those definitions. when you're trying to implement it within your work, like within your organization, things will be a bit easier, right? And some of these things will come for free. Like it will be already set for you. And the secrets and passwords, like passwords and client ID, I'll put them here in the notebook, but they shouldn't be in production, right? So use config maps and secrets as well. Just small. So I signed in with my mail. So great. We can run this one. Make sure that gcloud has configured my email. Great. And then we're gonna set the project ID. And now we're going to create the bucket. So if you're working on your local host, you're going to need gsutil installed. Otherwise, you can run it from Google Colab. You get it in the VM, and that's it. The bucket has been created. Let's make sure that we have access to it. And this is the part where some of you will get an error, I guess, because I wasn't able to add them to the IAM role. Now we're going to install Google packages. Let's run this. It will take a few minutes, a few seconds. But meanwhile, I'll just give you an overview. I ran this about 2 hours ago just to show you how it's going to look like. So if you guys remember the pipeline we've looked at in here. So this is exactly it, right? And whoever is familiar with Kubeflow probably can recognize part of the UI here. So we have the loading data step. And then this step outputs an artifact of type dataset. This is our data that we extracted. We can extract it from feature store. You'll see in a second that I'm just reading it from the web. After that, we're going to run a validation, like validate data step, which will give us a new dataset that has been validated and imputed, and there are no nones and so on. Sorry, I've never worked with a trackpad before. And then we're going to prepare this data. Preparing the data will probably we'll do just this train test split from sklearn, and we'll send the train data to a new step called train data. So this will be the Y train and the X train. And after that, Y test and X test to the evaluate model with the artifact that we have generated in the train model part. And so on and so on. I will go into each and every one of those later on with a bit more details. But eventually what we want to get is this deploy model to an endpoint, okay? And you can see that it's wrapped in a square because we discussed about making sure that the model is good enough for production. This is exactly the condition that will make sure that it reaches some sort of threshold. We will see what this threshold is and how I defined it in few cells right now. So great, after we got this running, some errors maybe with conjunction, it's all good. And we can restart the kernel. We must do it in order to get those packages. Now, after we restart the kernel, as you probably know, we don't have anything set up, so I'll just go a bit further up and run it again, those two. So authentication is not needed anymore. And we can go, let's clear this output. Great. If you're working with Jupyter now, like on your local host, you will need to run this one. So you will have, if you're working with your own GCP project, not the one I defined, maybe some of you are, you will need to run this one just to enable some of the components of GCP. Next, we're going to do, you know what, I have this cell again, so just we need this line. Sorry about this one. I had a few changes in the notebook in the last few minutes. So, okay, so we just need the Artifactory registry name. This is where we're going to deploy our image, Docker image that we're going to write. And then we can start and look at the actual code. Right now, 3 to 4 minutes to set the environment, and we can start and look at the actual pipeline, right? So what I care about the most in this cell is the Kubeflow imports. We're going to import 2 different types of objects. The first 2 are the compiler and the DSL. DSL is the domain-specific language. These guys will help us convert the code into JSON or YAML format, and then it will help us share this serialized pipeline in between different groups and teams and flows. So if we have 5 different data scientists working on, each of them will work on his own model, we can share the logic of extracting the data, for example, or just the template of the JSON file, and then they will be able to open it up, get the code, have their changes, and deploy it to production, or just keep working, and then you have some symmetric workflow with the ops part and the data science team. Now, the next few components, we'll see them in a bit, but these are decorators or some object that will help us work with Kubeflow and transfer data in between the steps. In case you guys are not familiar with what Kubeflow or workflow orchestration, really how it works. So each and every step in the way will be orchestrated and running in its own pod. Like Kubernetes will bring up a pod, run the logic that we have within it, output some file to file system, for example, do some other action, and then we'll take it down. And we need some, like this is the way that we can communicate in between steps. You'll see it in a second. The last thing here is the AI platform init command, which will help us define in the code that we're going to work in front of Vertex's API, okay, to deploy an endpoint and so on. Now, this is just the endpoint definition and pipeline route where the pipeline is going to run. It's a bucket and your username. And now we're going to focus on those two steps. So loading the data and validating it. So as simple as it could be, again, oversimplified stuff, but let's focus on the component decorator for a second. So this is one of the Kubeflow's object we just saw. What it's basically saying is that the next function will be, okay, so I didn't import it, of course. Okay, so what this component decorator will say to Python interpreter is that this next function would need a package pandas for this pod that's going to run. So it will pip install pandas, and you can give it a few more arguments, such as the image that you want to use, if it's a simple Python image or Alpine and so on. And you can also tell Kubeflow to export or to write this function as just as one JSON and not as part of the full pipeline. And I'm just thinking right now that maybe I'll stop here and show you the actual implementation of the pipeline, and then I'll go back to explaining this step because I think it's too abstract right now. So you can stay on this one. I'm just scrolling a bit down to show you. Great. So I'll talk about this one, and then we'll go back to the load data one. I'm sorry for the confusion. So this is the actual, this is how we define the pipeline. Basically, it's a graph with edges and vertices, and each one of the functions that we're going to write that being decorated with the component is the vertices in a single, and then we need to connect them with edges, right? So we have load data, that's the function we just saw. It's a component, like Kubeflow component. And then raw data will be a task that Kubeflow has defined. And then we can use that task's output to give it as an input to the next stage. And then we can write the logic here and pass through different parameters in between the steps. So a good example would be that if you remember, prepare data will split my data set into 4 parts. The X test and X train, Y train, and Y test. And then I have 4 different outputs, but 2 of them will need to go to train model, which is the outputs of X train and Y train, like we saw in the UI. And then for the evaluate model, we're going to send the X test and the Y test, but in addition, from the train model task, we're going to send the artifact. And I hope that makes sense. This is how I basically define the pipeline itself. And now we can go and look at each one of the steps, okay? So let me go back to load data. Great. Now, the use case that we're going to use here, if you have seen this one, is that I'm going to read Diamond's data set. I guess most of you are familiar with it. Basically, this is how the features looks like. And we will try to predict the price of a diamond based on some features like carat, cat, its color, X, Y, Z, dimensions, and so on. However, if you see here, I'm filtering all the diamonds that their price is less than 10,000. Therefore, When we reach the point where we have an endpoint out there, we can simulate real-world data and send the most expensive diamonds and see how there's a distribution shift, and hopefully Superwise will be able to discover it, open an incident, and trigger retraining pipeline. Okay? And then something in addition to it, there is a type hint in here, which is a bit weird. And what this actually tells Kubeflow is that on the fly, while this pod is up, there will be an output object of type dataset that will be allocated to that run. Now, this object will have few attributes. One of them will be a pass attribute, and Kubeflow will define some path within the workflow bucket, and then we'll be able to read and write data to it. So in this example, that's an output, so we're going to write data to it. And the next step, as you can see here, which is the validation data step, it's going to read this data set as an input object, and after that it will output a validated data frame. Okay? So I hope that makes sense. And again, packages to install only pandas. We're going to import it within our component, like within our step. And I'm not going to go over the code because I think, again, it doesn't really matter to any of us. We have used here very simple techniques of cleaning the data and making sure we have no nulls in here. Great. Now we're going to move on to the next stage. After we have a validated data frame, we're going to split it. We're going to move it to a prepare data step. We're going to split it into 4 parts. And then some of the data will move to train model and some of them to evaluate. Now, as you can see, it gets a bit more complex here. So we need the data frame as an input, and when you have 4 different data sets as an output. The component here is, as you can see, we needed another sklearn package to be installed. And then as simple as it can be. One thing maybe to mention is, as you can see, I'm using, for example, xtrain.path. Now, I don't know in advance what this path will be, but I don't care because all I need is to pass this one to the next step. So as far as these 2 steps are aware of the actual value, it's good enough to me. So I'm going to run it, and then we're going to move to train model component. We're going to use joblib. We're going to take the model to train, and we're going to serialize it using joblib package. And we're going to output a new type of artifact, which is of type model. Now, every one of those, they're pretty much inheriting from the same object. However, each one of them has different attributes that we can utilize, right? So model will have for example, performance attributes that we can write. It's going to have metadata dictionary that we can write some metadata to it, and so on. In this step, we're going to have some pipeline, sklearn pipeline. There's a differentiation between the two, and we have an imputation and column transformers, and we do some one-hot encoding, and so on. And we're going to train a random forest regressor. I already tuned it so it will be good enough. Not really me, it's from Kaggle, so thanks to Kaggle. And then we're going to train the regressor. We're going to set the parameters, have the pipeline in place. So first of all, we're going to pre-process the data that we got, make sure that categorical feature will be transferred to numeric and so on, so the regressor will be able to process them. Then we're going to run cross-validation. Again, for time efficiency, we're going to use CV equals 2. And then we're going to fit the pipeline to the xtrain and ytrain data. We're going to dump the model object into model artifact.path. We're going to use some compression because we pay to GCS on IOs. And eventually, we're going to write to that artifact the train score. So that's an example how we can use Kubeflow's object in order to save some more information. We're going to see how it comes into play in the UI. Last steps is the evaluation part, where we're going to run this one. And so we get an input of the model artifact, the X test and Y test. Model performance is the output of the metrics. We need it for the later on when we are doing the evaluation, making sure that the model is good enough for production. So we need to see if it was good or not. And an HTML is just an example for your reference if you guys want to add some cool pipe plots and so on to the UI of Kubeflow, and then you can share them and have some, it will be quite similar to how MLflow keep tracks of experiments using, like for the actual animations and plots. So again, I'm running very quick on the code, just very, like the most important ones. So we can take the model performance output object, and we're going to log into its metadata dictionary root mean square error of what's the actual calculation, and R2, and we're going to add, and then we're going to log the metrics of it. So we're going to see it in a few seconds, how does it looks. And then I'm doing some fig to base 64, so it will be embedded within the HTML. And I'm just creating an HTML content. I try to keep it as simple as possible, and I'm going to write this HTML content into the HTML object.path. Again, I'm just utilizing those attributes. Now, validating the data set. I want to see if there's any differences here. No, same thing. What do I mean by validation? We're going to make sure that the R2 score reaches some threshold. I defined here, like the most simplest one is that make sure that the new model metrics R2 score will exceed 0.95. The absolute value of train score will be smaller than 1,000. And that the RMSE of the last model will be smaller or equal to the new model metadata. Sorry, it's not the RMSE of the last model, it's the RMSE of the train model. So I want to make sure that from the training stage, when I used only the training data set, now I'm training it like I'm running it on the validation data set, I want to see that the more data it gets, there is an improvement in performance. Again, an oversimplification. And sadly, there is no Boolean value to return from Kubeflow pipeline components. So I'm going to write a tuple with true or false strings in it. Now, going back to the cell we've seen before, now we can actually compile those steps into one single object, and we can go ahead and run it. Okay, so we're going to execute it, and that's it. Now, it's going to run in the background, and we'll see it in a second. And what basically happens here is that we connected all the steps and validate model. Now, this is up until this part, this is usually what I would suggest teams to have their data scientists focus on, right? They will need to have this framework in order to implement their logic. The ML engineering part is still not in play because the more standards there will be in the data science team between the different data scientists, the easier it will be to create automation and productionize all of them with triggering in place. So this is a very flexible framework for them to work on. So maybe in the beginning, as ML engineers, we can work with the data science team to define those steps, make sure how we can solve some edge cases and problems. But as soon as we have those steps in place, it's simple. It becomes more simple to us to connect a monitoring, which we're going to do in a second, a monitoring platform, and in addition, deploy to an endpoint. Now, questions up until now? Wow, everything was clear. Okay, thank you. Great. So we're going to have a quick look on the pipeline we just deployed, we just ran, and there it is. I see 2 people are following me right now. Oh, one of them is me. And these guys are running right now, these pipelines. And one great feature that Kubeflow has is the caching, right? So as long as the JSON file that you compile is not changed up until some point, it will keep caching of the last stages. So right now we can go and take the pipeline that we just wrote, add some more logic to it, and still know that we're not going to run everything from the beginning, just from the last step that the pipeline stopped at. As you saw, the logic was not very complex, but this pipeline going to run for about 10 minutes because allocating VMs and there's a lot of overhead that we're paying here for very simple logic that we wrote. However, when you will implement bigger and more heavier tasks, you will feel that it's running in good enough time, right? So keep that in mind and don't get don't get scared because it takes a long time to run. And now we can move on to the next step. Now, the next step would be to connect Superwise to our pipeline. And this is where the actual engineering part, I'll say, comes into the picture. Those two next steps are going to be our responsibility, or my responsibility as an ML engineer. And as you saw, we have the condition that we saw before, and if it reaches that, that if it's true and it's good enough for production, then we're going to run a register model to supervise step, and afterwards we're going to deploy this model to an endpoint. So one of the prerequisites for the talk is to sign up to Superwise. In case I did it just 3 minutes before, some of you have seen me doing it. It takes 2 or 3 minutes to sign up. It's free, and you get up to 3 models. The community edition is up. You can monitor 3 models. And if you guys want, you can just do it right now and sign up. And this is how the platform looks like. What I care about the most right now, before we go into details, is to generate the tokens that we're going to work with, because we're going to write an automation that will generate a model in Superwise, a model entity in Superwise that will be connected to our model in production. So we're going to generate a token. We're going to give it a name, for example, workshop token. Okay, and this is one of the things I told you that we need to keep on our Kubernetes config maps and secrets. So it's going to produce me a client ID, which I'm going to take to the pipeline and put it here. And it's going to give me a secret key right now, and I can put it here. Great. Now this is the only two values that I need in order to use Superwise. Now, the next step is a component function, right? It's a step in the pipeline. It's going to get just regular arguments, which are simple to understand. The model name and the client and secret, and also a baseline data set. What's the baseline data set? Can be anything you think is similar, like it will be the most, how would I, okay, in this case, we're going to use the train data set as the baseline, and this helps Superwise to come up with different statistical metrics and understanding of how the baseline data looks like, and then it can calculate differences from the real-world data and have all those policies. If you define them, it's great, but we can get a lot of understanding about what goes wrong and why, and then we can produce you some understanding of what's going on. So another change here in the function would be that it's returning a name tuple, because I want to return multiple different, the model ID and the version ID of the model from Superwise. So I will be able to connect them in the last component of the endpoint itself. You will see what I mean in a few seconds. I will not go into this code as well. It's quite simple to understand, just a Superwise object that we're going to work with in order to understand what data types are in there and connect it and create a model within Superwise and so on. Now, let me make sure that those steps, okay, it's still running, which we don't care about. And then let's run the pipeline. Same pipeline as before, just with this context that has been added. So with the DSL condition that we defined from the validate model step, the deploy is true, then we can move in and go into that condition. And then we're going to run the register model to Superwise. As simple as that. We're going to use the exact same logic to run it. And we can see that a new step has been launched. That's called Superwise pipeline Itay Ben Haim. It's going to use the caching from the last one. So we just saw that it's still running the train model. It's going to start by running train model. And we will see in a few minutes that a new model will be signed into the Superwise platform. Great. Now, up until now, let me go back to the slides so we'll have some context. So we wrote a pipeline from data extraction all the way to model validation. We also have a model monitoring system in place, and now we need to connect them. The way we connect them, the model registry and serving, as I said in the beginning, we're going to write a small Flask application that's going to use some environment variables in order to have the model that model validation step has given us. And then we're going to wrap it around two endpoints. One of them will be a predict endpoint, and the second one will be health check, so Kubernetes will know that the service is good enough. And the second we have that, we can deploy it, like we can deploy it to an endpoint and serve it to Vertex, and we have it out there in the wild, ready to get feature vectors to predict on. So now the next stage would be a bit more hands-on niche, okay? You can go ahead and git clone those workshop branches from this model orchestration repo. And I already did it in the beginning. You find it. Great. I even changed my theme to light. It's the first time I see PyCharm in looking like that. It's weird. Great. So we're going to have a quick look on the Flask application. First and foremost, I think the Docker file, that's my go-to usually when I'm trying to understand and make sense of a new repo. All those arguments and envs are necessary only for localhost debugging if you want to run Docker build and make sure that our model is, that the Flask application is good for production. When we're going to use Vertex or the AI platform SDK of Google, we don't need it because we can define and inject environment variables from the SDK. We're going to use the requirement text, we're going to pip install it, and then we'll take the rest of the logic. These are the only things we need. So we need Superwise's SDK, Google Cloud Storage, Flask, and Unicorn. That's it. Now, when you're working with services in GCP, usually in the service account, you don't want to give specific users the permission of sitting out there all the time and usually the best practice is to have a service account in place. I guess most of you who worked with GCP knows how to generate one. You just go to the platform itself, IAM roles component, service account, and you generate one. I already did it in advance. So I think the first thing that I'm going to do, forgive me, that's the errors of Terraform giving you all like the permissions. So great, I'm going to look at the orchestration, and let me bring, you know what, I'll do it in PyCharm so it will be a bit more contextual. Okay, so the first thing I'm going to do is I'm going to copy the key file that I've generated in advance. So it's in here, I think, yeah, no, it's not this one. Workshop, resources, and then I have predictor service account, great, and I'm going to put it in the resources, great, and now I'm going to have here a new file. Now I'm going to move this file to be called creds.json because that's how the implementation expects it to be. So resources, predictor, I know that I could have done that in one step, but I'm just trying to make, okay, great. So there it is. We can see that we have all the things that we need in order to have our service account with the permission that it got in GCP. And now we can have a look at the service itself. So two modules in here. The first one is the service itself. As I said, we're going to have two endpoints. One of them would be the predict endpoint. It's going to sit on Diamond's v1 predict URL. And the second one is the health check. And now, you know what, before we'll move to implementation, there is an example here of how the payload looks like. So we're going to get instances of feature vectors. So it can be batch or it can be one each time. And then we have the predictor class. The predictor class, I already put in the logic for sending data to Superwise. It's as simple as doing just log records to the model ID I care about, and those are the records that I want to log into Superwise. And basically what my Diamond price predictor does is reading the model from GCS, from the Artifactory that I defined in the steps. I think I skipped that in the component, but I'm writing it to GCS, and then I'll be able to read it in here. And after we have this diamond price predictor instance in place, we can start sending predictions to it. So let's go ahead and start writing the logic here. So I gave a few, I put all the imports that are needed, so it's a hint. We're going to write it together. Feel free if you're working on your laptop and you want to implement a different logic. I don't care about it. You feel free to do so. So first thing, we're going to need a storage client, right? And so we're going to use storage client package, and then bucket name would come from the environment. Bucket name, great, as you remember. So it's this one, and I'm defining it in here so I can understand what bucket I'm on. Next thing would be to create the actual bucket that I'm going to work against. So it will be this one, and get bucket, I think. Why is it not completing anything? Okay. Storage client, get bucket name. That's supposed to be good enough. And we're going to use a blob bucket. I have some some safety net here. So great. So blob would be bucket blob of model, this one. Great. Now we can read from that blob. So with the temporary file as temp file, that's basically a function, and we can have blob download as file, temp file. Again, you have enough time if you guys want to implement it on your own. I'm just using temporary file because I don't want to leave traces on the temp file. 60, let's return the pointer to the beginning. Model equals joblib dot load the temp file. That's great. Let's return it. Great. So let me just make sure that we're good. Setting the model, we have storage client. Yeah, seems good enough. And now the prediction, if you remember, we're getting a list of dictionaries with the features and the value, like key value pairs. And let's see, so we're going to take the instances. So we're going to do input data frame would be PD data frame of instances. Great. And then we can, we're going to add a new series to it, and this would be self model dot predict. Yeah, and the input df. Perfect. And transaction ID would be self send monitor data of input df. And API output, and we're going to do, we have it like that. So transaction ID would be transaction ID, and we can have the predicted prices equal input df predictions. Great. Dot values to list, and that's supposed to be what we want, and we can return it. So everything I've done it is pretty clear and obvious, I guess, right? Any questions? Perfect. Now we can go back to the server. That's a bit easier, and we can use the, okay, so up here I use the predictor as a global variable, and we have the diamonds price predictor, which gets the model price path from the environment variables, and then create the instance of price predictor. And then we can go ahead and do predictions equal predictor predict instances equals request JSON, I think, instances, Great, and I'm going to return a JSON file of predictions, and that would be the predictions list. One sec. Great. And okay, yeah, I know what I'm missing. Great. Sorry, I hate to see it looks. Thank you. Predictions, and I'm going to need the transaction ID as well. And it's going to be transaction ID. And yeah, so let me make sure that I'm sending here what I'm, predicted prices, that's what I want. Great, so we have this one and transaction ID. Let me make sure that we have it written properly. Great, and now let's refactor it so it will look decent. Great, thank you very much. So this is the logic for the endpoint, that's it. We try to keep the endpoints as light as possible. And health check. Now health check is supposed to be just a response equal JSON file health. Yeah, just like that. I'm hoping you are not falling asleep. Okay, and that's it. So now we have health check in place, and we have the predict instance in place, the predict endpoint in place. We also copied what we needed, and we have here some logic for building the image and pushing it to GCP's artifact registry. But before I do that, we don't want to push any corrupted Docker images there, so we can have a very simple check to make sure that it's going to run. So we're going to do a Docker build. I have it here in advance. What we're going to do here is just Docker build and we're going to call it a local predictor. We're going to provide all the argument that it's going to need. I'll just have to change the model pass, I guess. I'm going to have to change many things, so let's do it together. So model pass would come from GCS. I have it here. Let's open a new one. I'm using my personal hotspot, so I'm sorry it takes a few seconds. Great, we can go to my pipeline bucket, and then we can have a look at a folder called models, and then I will have the models. Let's make sure that everything runs. So great, everything here succeed, which is great. In a second, we're going to see that Superwise has our model registered into it. And you know what? Out of time, maybe I can. Let's see. Yeah, okay, it's running. Okay. Workshop. That's the pipeline route. Okay, I'm not going to check it here. I'm going to trust myself that it's going to work. And if it's not, I already prepared a backup, and we have this Docker image ready with the same logic implemented. So all we need to do is just source the build and push image. When you will do it on your local host for the first time, it's going to take a few seconds because it needs to install everything. In this case, it's supposed to have caching in place, and if not, so we'll just let it run. And again, I'm going to show you, yeah, so it's running pretty fast. And then we can go to, by the way, these are all the steps that we had in our pipeline. Each one of them has a directory, and we can go in and have a look about their artifact and so on. But in a second, I'll show you the UI after it finished and how we can look at it and see some other stuff. But in here, we're going to look for the artifact registry. Thank you. And you can see that I already uploaded an image that we can use. Great. I think in my next workshop, I'm going to do it all open source and have it on my local host. Everything will work way faster. So, a action item for the next one. So these are the images. As you can see, I already have had a few, and this is the last one, pushed 2 days ago. So we're all good to go. And now let's just for time efficiency, I'm going to run this deploy, the last step, and we're going to look at the code later on. But I just want to have it running. And let me just see that it's got an execution. Great. Now, let's have a look at the pipeline. I'm going to look at Knife's one, because it's more interesting than mine, for sure. And we're going to look at the interesting artifacts, what we care about, okay? So if you remember, I said that the model object of Kubeflow will get a URI on the fly, which I'm not aware of. So that's an example of how it looks like. It's still there, and we can log in, and we can send it to other people. So this is where the model has been, where the model a job lib object has been written to. And in addition, if you want to look at some, okay, one cool metadata property that we also logged is the train score. And you remember if I said that if it's the absolute value will be smaller than 1,000, then we're good enough for production. So in here, we can see that our model missing in on average on 447 US dollars when he's predicting diamonds. Now, Y test and X test gets URIs as well, but cool thing would be the URI of the HTML. So we can look at the view HTML. We can look at it and have a look at how the pipeline has generated. This is how basically our model behaves. So you can see it's a bit missing on the expensive ones, but generally it looks pretty well. Like we can move on and deploy to production. In addition, we have this model performance object, which has an R2 score of 0.96. So it's also exceeding the threshold of 0.95 we defined. And the RMSE is 431. So looks like our model is good enough for production. The validation step finished with some other metrics on the entire data set. And we also deployed, sorry, I don't know what I just did. Again, I'm not a big fan of the trackpad, I'm sorry. And we see that register model to Superwise already finished. These are the values it got. And the model ID would be 39, and the version ID would be 21. It doesn't really need to tell you anything right now, but if you'll check Superwise's SDK, you will see that because we're an API-first platform, we care about IDs, and this is how you can work with our REST API and SDKs in order to use to run some to use the SDK, basically. Now here you can see the model. I already signed it because me and another guy, someone here, also ran the pipeline. So we have 2 versions, and we can click on it, and we can see what Superwise understood about our model so far. So currently there's no production data. I'm going to look at the analytics page first and foremost. There is no data in the production. Superwise supports segmentation, so if you have subpopulation within your data set and so on, you can have a look and see different slice and dice and get understanding about them. Now we're going to look at the baseline data, and you can see that here are the features. Superwise understood that caret and depth are features. This is their distribution. You can click on it and look at it from many different perspectives. Features like categorical features will have their values in here. And in addition, we can see that we have label, the price is the label, and the prediction will be the prediction feature. Okay, this was in our baseline data set. Now there are many other things here, but I'm not trying to sell you Superwise. I'm just trying to show you a concept. So let's put in a policy that will monitor our feature distribution in production. And in case there will be some drift in it, it will trigger some webhook. So I'm going to click on create policy. And again, the internet is quite a bit slow, so things are moving like slower than expected, but bear with me, please. Please start. Maybe I'll try to use this one. Okay, looks way better now. And now, out of the box, Superwise is giving you many different policies and templates. We care about feature stability, as we said, and let's click on edit. There are multiple stages when you define a policy. I will give Superwise the freedom to define the thresholds. It's like time series anomaly detection, so I'll let Superwise decide for me. It's going to run on a daily aggregation basis on all the data set. You can choose all segments, the entire data set, if some record is not within a segment, and you can run on specific segments, and we can create a cron job to run that monitoring policy. Right now I've exposed an endpoint that will trigger the policy notification, and now I need the integration channel. How will Superwise know that who to notify and what to do? So I'm going to create a new integration, and I don't care about email, Slack, and all those. I care about the webhook one, and we call it a retrain webhook, right? And then we need the URI. In your organization, you're going to have a Flask application or some microservice out there that will get this webhook, understand some stuff out of it, and will trigger like a more strategic retrain. But it's out of our scope right now, so I did a cloud function in advance. I'm going to show you how it looks like. Just it will listen on this webhook, and then I will be able to trigger a retraining pipeline, and we need cloud func, and it will find it, hopefully quick enough. Makes everything so slow all of a sudden. Oh, we're in development, sorry. We should move to the project of workflow workshop. I'm sorry for it. Go here and look for I just need to bring the URI from GCP. This is why I really need it. Maybe I wrote it somewhere to myself. No, I don't have it here. Oh, I do. Perfect. Thank God for notes. Great. So this is the URI already defined. And we can go back to Superwise's platform, and we're going to put it here. We're going to test it that it's the right one. And again, the internet is a bit slow, I'm sorry. Okay, great. So test messages delivered successfully, and then I can create the integration. Now we can connect it as a webhook to the policy, and again, and let's call it retrain policy. Great. So, great. We have it. Pretty much our model is robust, like our production service is robust, and we can start in simulating real-world data and see if it is working. Now, before I do that, if you guys remember, I launched a step to deploy to an endpoint. And let's go back to pipelines. It's still running. It's probably going to take, this one is the heaviest or the slowest task that I have here. It's going to take about 15 minutes at least. What GCP is doing under the hood is making sure that the service is stable enough, so it's making a lot of health checks, allocating different VMs to make sure that some network IOs are good enough, and allocating a mean IO driver to make sure that you can talk to the GCS storage using a unique, like a specific interface. We don't really care about it. But in order to save us time, I already launched in advance an endpoint. You will see that this endpoint will be updated once this pipeline will finish, but right now we can move on. Just the last step, which probably needs a few more words, I skipped it, would be deploy model to an endpoint. It's going to get the project of GCP. Location is the region. Bucket name that is going to read the model, the bucket name that we actually passing through to the image. Timestamp, so it will be unique. If many people here would have run it. So secret client, like client ID and secret, the model ID and version ID. So we will know to connect them to the Superwise's specific model and version. And then the model that we're gonna send, again, it's generated on the fly. And the vertex model is actually the output. This will give us the endpoint that we can talk to and send requests to. Again, I'm running on the logic here. The notebook and the repository will be available to you. You can look at the code and try to make sense out of it and reference it to your usage. The last thing would be the ML pipeline, exactly the same as before, same DSL condition, log to Superwise, it's all cached. And the last step would be the deploy model to an endpoint with all the variables I just discussed. This is the image that we're going to use, come from the artifact registry name, diamonds predictor, is going to use the latest one. Something to bear in mind, which is I think very important, is the ML pipeline JSON that has been generated during the, it's in UTC time, I think. So this is actually the state, like the serialized JSON of the entire pipeline. And we can use it and share it among different teams and have it, every different components written, but other components will be shared. Yeah, and then I ran it, and it's all good. Now we can go ahead and simulate some real-world data stream. And what we're going to do, we have the endpoint ID. It will be the output of the step that is currently running. I already know it because I deployed one in advance. And then we have two data frames, basically. Okay? One of them will be the expensive data frame. So I'm going to take the more expensive ones, bigger than 10,000, and I'm going to sort them in descending order by price. So the first record will be the most expensive price, and the second one will be the second, so on. And another data frame, which will be exactly like I trained. And then I have a counter of 28 days, and I'm going to send chunks of 500 feature vectors for every prediction. While in the last 10 days, I'm going to use the expensive data frame to send the instances to predict on. And you're going to see what I mean in a second. Now it's going to start running. From the 13th of May, the average will be 2,233. And then it's going to start running. When it will reach 10, you will see that there's going to be a big bump. So we're going to see a very homogenic graph. And then all of a sudden, the burst. It's going to reach the highest levels. There's going to be a distribution shift, definitely, so we hope. And then it's going to converge back because it's in descending order, so it will start decreasing. And you can see that 14, 13, building the pressure, 11, and now 10. Great. So from 4,000, we reached all of a sudden 18,000. So definitely those diamonds are expensive because their features are different, and we need to understand what changed. Now, in order for Superwise to see it, we're going to need Superwise to run the cron job that scans all the production data that we just sent and analyze according to the policy the time series anomaly detection and trigger the training webhook. Now I exposed in advance the triggering, and of course that I need the token, so I'll just grab it from here. Don't mind if I give me a second just to get the JWT token. Let's click on this one. And you know what? Activity log is interesting. I think I want to show you. And here is the token. Great. You can paste it here. Make sure that this is gone, and then I'm going to click on this one. Great. This is, ignore the output. What's happening right now under the hood is Superwise starting to scan and analyze all the features that you got in production. The activity log section will show you all the transaction we just got. So we have 2 regression diamonds model. We got 500 records, many different records of bulks of 500 feature instances, and all the transaction passed, and we have it within our data. So this is probably going to take about 5 or 6 minutes, and I think that's great time for questions. I'm going to ask you questions if you're not going to ask me. Okay, great. So I already prepared an environment that got an incident, and you will see in 5 or 6 minutes, I guess, we will see the retraining pipeline being initiated, like executed without us doing anything. But meanwhile, I'll show you how Superwise will show you the incident, right? So we have exactly the same environment in terms of data and model, so I already did it for us. And there are incident page, and we're going to look at the closed ones, because when we define a policy and we have a solution for a policy that realized an incident, then Superwise will understand that we solved it, and it will move it to a closed incident. And then we can see the retrain after drift. This is like the rest of it is from the demo model. This is just for new users, but this one is exactly what we did, and I'm going to show you how it's going to look like. So as I said, it's going to be in the last 30 days. We're going to see pretty much, this is the feature of color, this is of carat, this is of X dimension, and this is of Y dimension. And you can see that exactly as we thought, we're going to see this graph of values that it pretty much expected, and all of a sudden there is a big bump. Superwise understands that there is a drift. And notice maybe something important to emphasize here. There are 3 ways to understand if your model is misbehaving. Now, one of them would be to compare the performance of the model, trying to compute the RMSE of the production vs the label vs the predicted values. One of them will be to understand like the entire data set, but on the entire feature vector of both the prediction and the features. But the disadvantage of those two, while they're very common, the disadvantage is that we necessarily need the ground truth. We need the label itself. And sometimes in different use cases, we're not going to have the actual ground truth. Imagine I gave an example of a bank giving a loan. Whether we approved it or not, until we will know that it was approvable or it wasn't approvable, if our model was right or wrong, years can pass. And then until we realize that our model is drifting, something broke. We might have lost our business, right? And one of the great takeaways, I think, from Or's talk yesterday about retraining strategies was that you can actually measure only the features distribution drift, and it will give you an accurate point of view of what's going wrong. Because if your features are drifting, most certainly you're going to have a drift in the actual predict value. So that's a great way to think about it. And this is why I didn't choose a specific feature for Superwise to monitor for me. He understood it, but you can also define specific features, and then the calculation will be shorter, and you can have more optimized compute to recognize what went wrong. Let me see right now if we have a retrain in place, if it has been triggered. Still no. Again, it takes a while because many calculations are doing under the hood. Maybe I'll show you one last thing on the production data. So right now we have production data, so Superwise gave us a look on it. And we can also see out of the box a few matrices. We can also configure our own custom matrices. But you get many different distribution shift of features, of labels. You can choose which features you want to create a KPI for, and so on. Now, we have about 20 minutes left, so I will run the cloud function on my own because I don't want to waste a lot of time, and I want to leave some time for questions and some talk maybe. Maybe we can discuss use cases that you guys are dealing with right now and think about usages as well. So I'm just going to run gcloud function called retrain.